Hello everyone. In this lecture we are going to learn about NACE MR0103 in detail. Our flagship courses are Master Static Equipment Design and PVE Light, ASME Section 8 Division 2, and Master Welded Storage Tank, as per API 650. We have curated courses to suit your learning needs. So do visit our learning platform for more details on scutoid.thinkific.com.
So when we say NACE MR0103, which kind of services we are talking about? Are we talking about the production of oil and gas? Are we talking about upstream, downstream, midstream, production, refining? What exactly the NACE 0103 becomes applicable for? What is that we are talking about? So we are talking about refineries. Okay. We are talking about refineries. Okay. Not the production part. Okay. So when you're talking about NACE MR0103 requirement, see, our intention for this session will be to take out whatever important things are there from the standard. Okay. You may not be able to cover it in very, very detail because it's a standard which is still evolving. Still lots of work is going on, and there are lots of factors which influence the material selection. Okay, so can you give me some factors which become a point of attention in terms of refineries, or when we talk about NACE? What are the things which are troubling for the material selection? Why we are talking about sulfur content, means of H2S, means of sulfur as a ion which is mixed with the water, wet H2S. What about other thing? Carbon content. So limiting the carbon content. So here we are talking about the factors which influence temperature, pH values, very, very important. Stress. What is the stress level? Okay, because we are going to talk about SSC, sulfide stress cracking. Okay, that means sulfur is there, stress is there. Okay, and if both are there, there's going to be cracking. Okay, and definitely these things are influenced by presence of temperature, by pH values. Okay, so we'll talk about them or the influence. So when you see the lots of variables, that is like partial pressure of H2S. It may be the sulfide ion present in the liquid form. It may be chloride ions. Okay, chloride ions is more common in production. Okay, when we talk about the upstream, when you talk about MR0175, that time chloride will be mostly found. So percentage is more in upstream. When we come to refineries, the percentage will be normally lower. Okay, so like I said, there are multiple factors. So partial pressure of H2S, you have chloride ion, you have temperature variation, you have pH values variation. Okay, now among all these factors, if one factor is exceeding or it is in a very high percentage, then it's easier to select the material. Okay, do you get what I want to say? Like, let us say chloride concentration is very high. Rest of the parameters are either not there, like H2S is not there, or pH value is neutral. So only chloride concentration is very high. Then it will be easier to select the material. When I say all the factors are mixed, many of them are high. You have high partial pressure of H2S. You have a pH value which is quite acidic. Okay. You have a very high temperature. You also have chloride ions present. You may also have cyanides present. Okay. Then it becomes really, really challenging. Okay. So Is it making sense to all of you? Right. So what we are going to talk about. So if the parameters, one or two parameters are exceeding, it will be easier for us to do the selection. So we will be learning some good practices, which material will be useful for which condition. Okay. So definitely the depth of this NACE is very high, and still lots of development are going on. So if the things are complicated, we may have to consult. Whom we have to consult? If lots of these factors like pH is acidic, you have chloride, you have cyanide. Okay, you also have partial pressure of H2S very high. Who will be giving the final judgment about the material selection? Who in the company will be the authorizing figure for that? Any one of you? Corrosion engineer, or we also call them material engineer. Okay, that is the common term which is used in oil and gas. Okay, so corrosion or material engineers, these are basically metallurgists. Okay. So they also use lots of software. Okay, and with that, they predict for certain environment, varying the percentage, they'll be able to know what will be the influence on different material. Okay, so with that, let us start. So our learning objective first will be starting with the key differences. Key differences between what? 0175 versus 0103. Then we'll talk about type of wet H2S cracking. What are the different types? Okay, mainly we'll talk about two types. There can be multiple, but we'll build upon that. Environmental threshold. Okay, what is the limit? So when we're talking about 175, what is the limit? When we say 103, what is the limit? What is the threshold? The partial pressure of H2S, chloride concentration, cyanide. So we'll talk about that. Then obviously the material selection, like if I'm selecting carbon steel, two things we'll be studying. One is if I'm selecting carbon steel and if it's NACE 103 is applicable, what are the limitation on the material? That is first thing. Second, what is the limit for use of 103? Make sense? So standard does not talk about very hard limits. So always remember that. So whatever figures I'll be giving, that will be based on experience and give you at least some judgment. Okay, because unless we draw a small line, even though there is no line, when standard has given very clear cut requirement, that it becomes really easy for everyone. Okay, the things become difficult when there is nothing given. Okay, like if we talk about uses of carbon steel, there is no upper limit given for partial penetration of H2S, partial pressure of H2S. Okay, so H2S partial pressure, if I talk about minimum, I think you'll be able to give that. What is the minimum partial pressure of H2S after which the NACE becomes applicable? 0.3 kPa. Okay, absolutely right. But there is no upper limit. Okay, so that is indicated somehow. So we'll be trying to figure out at least not a very hard line, but at least soft line. Okay, so we'll talk about these two factors. Then we'll be at the end, we'll be taking some examples for the condition. So I'll cite out the different condition and you will be telling me which material to use. Do you think that will be good? I'll give you 4 examples. So 4 condition. And you will be giving me in that scenario which material will be useful. If you think that is going to be useful exercise, give me a thumb in the chat. If you're not giving, that means no, if you're not excited, I'll try to skip that. So do you think that will be interesting example to see. I need more thumbs to see if really people are interested to seeing that example, or I'll skip that. Okay. For me, that is going to be highlight. Okay. That is going to be the learning part for you. If you are clear with the last 4 examples which we take, if you understand that, you will have a soft line drawn. Okay. This is the condition. This material will be suitable. Okay. For this condition, this material will be suitable. So a soft line, I'm not saying it's a very hard line because there are variables. Okay. We'll be taking small variation and we'll try to understand which environment is good for which material. Okay. Thank you. Thank you. Glad to see lots of thumbs up and yes, okay, in the chat. Great. So let us start with the first point, key differences. Okay. So first, the key differences in terms of scope. Okay. So can you give me in terms of scope, what is the difference in 0175 and 0103? One of the part we have already covered. In terms of scope, NACE 0175 is applicable for upstream, midstream, downstream, production, refinery. Upstream, which is nothing but the production, right? So oil and gas production, upstream. Okay. 0103, you can call it as midstream or downstream because refinery normally it will be called as a midstream. So sometimes it's called downstream also. So petroleum refining and gas plant process. Okay. So process plant which are generating different types of gases, they are also 0103 may become applicable. Okay. 0175 also used for onshore production, while 0103 is mainly for refineries and petrochemical plants. Okay. That is the scope difference between the two. What about environmental differences? Anyone can give me? When I say environmental, I'm considering the partial pressure of H2S. Okay. So do you think both of these standards, you spoke about 0.3 kPa pressure, right? So our 0.3 kPa NACE 0175 becomes applicable. Do you think the same limit is applicable for 103 also? And other factors like Morino is mentioning production, there will be chlorides. Refinery, you may have cyanides. Okay, chloride will be either no or very less. Okay, so first about H2S partial pressure. So if you talk about partial pressure of H2S, 0.3 kPa above MR0175 becomes applicable. pH value normally 6.5 and less. Okay, so the oil production pH value is normally towards the acidic side. It also because of the presence of CO2. Okay, so CO2 also drags down it to more acidic. Okay, you may have chloride presence most of the time more than 50 milligram or 50 ppl if we consider the density equal. Okay, so mg per liter will become ppm. If we think about 103 refinery services, partial pressure of 0.3 kPa is what is given here also as a limit. But here, not only partial pressure, but also the sulfide in the liquid or the service fluid. That is also given. So that is 50 ppm, okay, in terms of weight. So that is the sulfide which is there in the liquid condition, while the partial pressure is the pressure. Okay, it's in gaseous state. Okay, MR103, either it will be very, very acidic or it will be very basic. Okay, most of the time it will be towards basic side, more than 7.5 pH. Okay, that is also because of the cyanide which are present. Okay, that makes it more basic. Okay, so it is normally at the extreme. Very rarely you'll be having 4 to 6 pH value for 103. 0175 also addresses CO2 because that is very prevalent in production. 0103 does not talk about CO2. Okay, because it is dominated by H2S. Great. So we talked about scope, we talked about environment, talks about material requirement. Are the material which are used for 175 same material are used for 103, or it's a different? So if you see, 175 is having or using a very broader range of material. Okay, much broader than 103. Even if you see in application wise, it may be using most of the material, like common material which we generally use, carbon steel, getting used in both of it. Okay, duplex used both of it, both in 175 also and 103 also. Okay, so corrosion resistant alloy, which is basically we take as SS, duplex, or nickel alloys like Inconel, Incoloy. Okay, these are the common material which we are using. So if you think about these materials, then they are common in both of them. Okay, 175 also have them, 0103 also have them. Okay, so commonly used material, not very different in both. Yeah, so that is the basic difference. Now we'll build more when we talk about the application. So we'll see that. Now, types of wet H2S cracking. What do you think is the common cracking phenomena in H2S service? Give me that in chat. What are the common cracking phenomena? SSC, we talked about that. What is second? SSC is what? Sulfide stress cracking. Blistering, very good. Hydrogen blistering. Then HIC, hydrogen embrittlement. Then you have SOHIC, stress oriented hydrogen induced cracking, and SOHIC, stress oriented hydrogen induced cracking. Okay, so first one. Okay, Vasundhara is saying previous slide. Just a minute, guys. So this is the slide. Okay, I'm not writing all of it, but yes, I'm not giving you very hard boundaries. Okay, so most of the material are pretty common for both of it. Okay, thank you, Bhargav. And so don't worry about this. If you are attending this webinar, mostly you'll be getting the recordings also. So you don't have to take a snap, or even if you're writing it down, very good. Even if you're not, don't worry. Okay, focus on whatever we're talking about. Adrian will talk about that at the end. Okay, with how you will be able to get the certificate. Okay, so we'll discuss that in the end. So type of wet H2S cracking, the first one is sulfide stress cracking. Okay, I have mentioned only to have ignored HIC and SOHIC. Why? Because SOHIC is very rare. Okay, very rarely it happens. And the second thing is, very few development has been done in terms of SOHIC. Okay, even if you see 0175, it mentions that statement that still it is getting developed. Okay, the phenomena is not widely known. It happens very few equipments. Now, so that's the reason I've kept two things, and among these two, I'll try to clear both of them. The difference between both of these, SSC and HIC. Okay. SOHIC is also similar to HIC. There's a small difference. Now, what do you think is the difference? What is the reason for SSC? Why does sulfide stress cracking happens? What are the reasons? Give me that. What are the reason for SSC? Why does it happen? High temperature. What else? Welding, cold forming, hardness. Yes. Okay. Blistering is different. Okay. SSC is different. Okay. But the reason why it happens, that is pretty common. Okay. So let us try to understand how does it happen. Okay. So there is H2S present in the environment. When it get in contacts with H2O, it becomes wet, and it get disassociated with hydrogen ion and sulfide ions. Okay. When it get disassociated in hydrogen, it gets absorbed in the metal. Okay. You can see the metal ions, okay, having positive, it goes and get embedded into the material. So it, hydrogen being very, very small ion, it fills the void which is there in the material. Okay. In the structure of that material, there are voids. So hydrogen fills that. By filling that, it makes the material more harder, okay, and prone to cracking. If the material become hard, it will crack. Okay. Now, the very interesting point is that when the temperature rises, the phenomena of hydrogen getting into the material becomes higher. Okay. So if you go to the 100, 150 degrees Celsius, more hydrogen will get absorbed in the metal. But the cracking does not happen at high temperature. Cracking does not happen at high temperature. Cracking happens at normal temperature from 20 to 60 degrees Celsius. Okay. So what happens? You have taken the vessel for operation at high temperature. That time, your voids are filled with hydrogen ion. Material has become hard. Now, when you come back to normal temperature during shutdown or maybe for maintenance, that time your equipment will crack. Okay. So that is what happens in sulfide stress cracking. Okay. Now, see, when we talk about sulfide stress cracking, okay, it's not only the sulfide which is critical. Okay. So that is where your SSC and HIC are different. Okay. HIC also produces same result, but now we'll talk about what is the difference between the two. Okay. When we talk about sulfide stress, stress is also coming into play. When we talk about HIC, stress is not relevant. Okay. Even without stress, your material will crack in HIC. Okay. While in sulfide stress cracking, you need stress. Okay. So cracking happens in the perpendicular direction of the stress. Okay. Consider this as a vessel, and this is the line which I have drawn. Okay. I hope you're able to see that. So this is the circumferential direction of the vessel. So material will crack in the perpendicular direction. You can visualize if the stress is higher, the crack will propagate in this direction. Okay. When we talk about HIC, the crack happens along the circumference, okay, in the same direction as the stress was, okay, parallel to this circumferential direction, parallel to the highest stresses points. Okay. So that is the difference between HIC and SSC. HIC happens without even stress, okay, only because of the hydrogen embrittlement. while SSC is due to sulfur and also stress. Great. Does it make sense to all of you? Have I made it clear? SSC and HIC? Yes, due to pressure, Kasif. Okay. Due to pressure, if there are residual stress, it will make worse, right? That is why we try to try to soften the material. If already there are residual stresses, it will get worse. Okay. Yeah, we'll talk about how we can avoid. We'll talk about what are the limitations should be imposed in the material so that it is minimized. You can definitely not avoid completely, but definitely you can minimize that. Okay. So moving forward. So when we talk about NACE 0103, NACE 0103 only talks about SSC. Okay. It does not cater to HIC. So when you are applying NACE 103, it is only applicable to SSC. Only deals with SSC. Okay. HIC, it does not deal with. Okay. Or it is not still evolved, may not be evaluated. So it only one type of H2S cracking, which is SSC, is what 103 deals with, while 0175 deals with both of them. Okay. Yes, Vimal is saying during shutdown there won't be any stress present. There don't, because there is no pressure. So that time HIC will be more prevalent. Okay. If it is cracking, it will crack because of HIC. Or when you are coming down, during the coming down, when you are at 60 degrees Celsius and still there is a pressure. Okay, we have not relieved the pressure, only temperature has gone down. That time it may happen. Okay, so it will only happen. SSC will happen when both of them are present. HIC will happen when one of it is there. Okay, only hydrogen, not stresses. Okay, hope it makes sense. Okay, now what are the threshold for SSC? Okay, now we'll talk about SSC because we are talking about 103. So SSC is more discussed and more explored phenomena. Okay, SOHIC, HIC is still getting explored. Okay, so frequency of SSC is very high. So that is the reason it has been evaluated more, and we have more record of that. HIC and SOHIC, very less records are there. So mainly we'll see the rules for that. So environmental threshold for SSC, if we talk about partial pressure of H2S, if the partial pressure is more than 0.3 kPa, that means it is passing the threshold. Now 103 will become applicable. If we talk about pH value, both acidic and alkaline, both are dangerous. Okay, so alkaline, you will have different kind of stress phenomena, which is called ASCC, alkaline stress corrosion cracking, and in acidic you will see SSC. So both of it is critical for SSC. Chlorides, normally in refinery it is very, very less, but still it may be present. Okay, so when we are talking about chlorides, definitely stainless steel duplex becomes of less use because stainless steel will not have or show good properties with chloride if we have high ppmg. So we'll talk about that, the limits and all, but generally carbon steel will not have any problem with chlorides. Temperature, so normally the cracking phenomena will occur at 20 to 60 degrees Celsius. The hardness, okay, and the material becoming hard, absorbing your hydrogen ions, that will happen at high temperature, but it will fail during the cool down. Okay, failure happens at that. Great. Now let us talk about carbon steel, our favorite material. What is the limitation for that? Okay. So before limitation, what exactly if you are using, let us say that NACE 103 has become applicable. If we are going to use carbon steel, what are the requirements which we have to follow? You might have already studied in 175. What are the things which we do? Or many of you may be familiar with the criteria which we impose when there is a NACE applicable, because we have to follow this. So most of you might be aware. So what is the requirement for heat treatment? Is there any requirement for heat treatment when you're using carbon steel? Does the material needs to be heat treated? The answer is yes. We are not talking about PWST now. It's in the material condition when you are purchasing the base material. Answer is yes. What type of heat treatment you will be doing for carbon steel? Normalizing. Absolutely fine. Okay. So material has to be, first of all, hot rolled. You cannot have flat rolled material. It has to be hot rolled. So either you do annealing or you do normalizing. Okay. So that heat treatment, any of that heat treatment will be required. When we talk about weld hardness has to be controlled. Okay. So why we are controlling hardness? Because that is the problem for SSC, right? So that is the single problem for SSC. Material becomes hard. So you want to have, or you want to use a material which is less hard. Okay. So we control the weld hardness. How we can control weld hardness? The developing the welding procedure by which you get very less hardness is very, very difficult. That also can be done. Okay. That can be achieved. Like Farhan is saying, don't do sudden cooling, maintain preheat, post-head. But that will be very elaborate welding procedure. Okay. So code does not ask that directly you go to PWST. Code says that if you are able to limit the hardness below 200 HBW, okay, now that is close to 22 HRC, little less than that. So MR10175 gives 22 HRC, which most of you are posting. 103 gives in HBW. Okay, I don't know why they are using different terms. Maybe because if you convert 200 HBW, it becomes a little bit lower than 22 HRC. So the hardness requirement is further limited in 103. Okay. And it refers 1472, another specification for that. So if you are able to qualify the welding procedure, after which you are getting less hard weld, then you don't have to do post-weld treatment. If you are not able to control the hardness, then you'll be end up doing PWST, controlling that by doing post-weld heat treatment. Okay. Normally, carbon steel, you will be avoiding where you have high cyanide or pH values more than 7.6. Become difficult for carbon steel material. Okay. Now, use case, mostly for H2S service, it becomes a default choice. Unless one of the key parameters like either cyanide is present, or there are few, we'll talk about them when we try to draw a line for the users. So if nothing has been given, your carbon steel is the best material to go with. It's also cheap. Okay, you can control the hardness by doing PWST, so no problem. Okay, so we'll see what are the limitations. One limitation you can see here is high cyanide, and the other if you have very high pH value. Okay, or even otherwise, if it's very acidic, less than 3.5 pH, that also becomes problematic for carbon steel. If you talk about stainless steel, austenitic stainless steel, 304 or 316 grade, that has to be solution annealed, hardness control to less than 22 HRC. Avoid when it is environment which is controlled by or dominated by chlorides. Okay, if Prin value is more than 40, then you can use. Duplex also, Prin value greater than 40 is always recommended for NACE 103 application. So this also has to be solution in it should be even the chloride content is little bit higher, it can take that environment. Okay, it is better than austenitic stainless steel in chloride environment. Martensitic, that also can be used. Again, heat treatment which you'll be using is quench and tempered, and hardness should be less than 22 HRC. Next, and the topmost, nickel alloys. Inconel will come into that. So hardness limit is a little bit higher. You can use 3547 HRC for 6625 Inconel. Use case, you can use it for very high H2S partial pressure or very high chloride ppm, or even if cyanide is present. In all the cases, you can use nickel alloy. So that is the topmost choice. It's also costlier. So this will be the end result. If you're not able to get carbon steel or SS or duplex, then you'll go with nickel alloys. Now I'll try to just summarize the different things which you have learned. So this table will make it very clear, okay, that which is the limiting factor. Okay, now I'll talk about these things, whatever we have covered earlier. That was the things which you're able to get in the standard, or maybe able to get in the specifications which you read from the client. But now what I'm going to present is the summary of everything. Okay, so this one slide will clear lots of your doubt. Okay, and try to draw a soft lines for the users. Okay, so what I'm going to talk about is, first I'll talking about the material like carbon steel. So what is the limit in terms of partial pressure of H2S? What is the limit of pH value? What is the limit of chloride concentration? What is the limit for cyanide? Okay, what is the limit for temperature? All that we are going to talk about. Okay, so let us start with the first one. Carbon steel. Partial pressure of H2S should be more than 0.3 kPa. pH range, mostly it is, if the H2S pressure is low, then you can take even all the range of pH values. Once the H2S pressure rises, okay, if it is closer to 10 kPa, then you like to have a neutral pH value. You'll not like to have cyanide. Cyanide anyway, it's a no-no for carbon steel users. Temperature, mainly 20 to 60 degrees Celsius. Okay, you can go up to higher temperatures also, depending upon the partial pressure of H2S which is there. So for carbon steel, the limiting factor here, what we can say is the cyanide. Okay, let us talk about stainless steel. For stainless steel also, H2S partial pressure for all the levels is perfectly fine. Now here in chloride, okay, if I put a value of chloride ppm, okay, if I say 50 parts per million, okay, in terms of weight, then in this case, you don't have any limit on pH value. You don't have any limit on the H2S. Okay. And again, one more thing I like to highlight, that this summary table, I'm trying to make it for both of them. Okay, 175 and 103 for both of them, considering in some cases, if you are 103, cyanide will be more. If you are using 175, your chloride will be more. Okay, so it will cover the uses of both of these standards. Okay, so when we talk about 50 ppm or 50 milligram per liter quantity if you are talking about, then you don't have any problem in using austenitic stainless steel for all ranges of temperature. No problem with any pH value. Okay. No problem with H2S partial pressure. Now, if my chloride content is more than that, then directly your H2S pressure requirement, your pH value, okay, everything, even the temperature range will come down. Okay. So we'll see that also. We'll talk about that. What is the few figures which I can show you? We'll talk about that. For duplex, mostly cyanide you need to avoid. Other than that, it's also have a pretty good fair uses with all the different H2S partial pressure. If you have high chloride, then the partial pressure will be limited to 20 kPa max. Okay. Even austenitic stainless steel, if your chloride is very low, then you can go to high kPa value of partial pressure. If the chloride content increases, your partial pressure goes down. Okay, so one of the parameter can be higher, other has to be in very low condition. If we talk about nickel alloys, again, nickel is the only element where even high cyanide presence may be tolerated. Okay, so if you have very high cyanide, if you have very high chloride ppm values like 1,80,000, okay, or that kind of figure, 2 lakh chloride ppm presence, then only you can use nickel alloys. You will not be able to use duplex or austenitic steel. Okay, so that is a very rough table. Now I'll build upon that. So don't think that this is the end. When we take the examples, I'll try to go into a little bit one step further to this and try to draw some more lines. Okay, I hope you are ready for that. Before that, let us see some conclusions. So carbon steel is the default material which you can use. Only thing which you have to control is the hardness. Okay, weld hardness, which you can do by post weld head treatment. Okay. Now, if there is a cyanide or high percentage of H2S partial pressure, like it's going more than 100 kPa, then you have to upgrade to SS. Okay, carbon steel is normally limited to 100 kPa. 100 kPa is kind of limit. It's not directly given, but that is a very high percentage of partial pressure of H2S for a carbon steel material. Okay, so there we change to stainless steel or higher alloys. Okay, nickel alloys, that is good for high chloride, high cyanide percentage. Okay, so basically whatever lines we are trying to draw, okay, the decision is based on how that material will behave in the particular environment. Okay, and definitely the environment may not be such that only one element is higher. It may have with variable element, and when that happens, it becomes really difficult to select the material. Okay, if only one is higher, we can make a decision, but if it's not, then it becomes really, really difficult. Okay, now before we take the example, which will clarify most of the things for you. So, first example. Okay, now forget about chat. Just for hold down. Let us see the question. Okay. Thank you, Fatiq Vasant. So let us now focus on the example. Okay. So we are going to clear or draw boundaries for uses of material. Okay. So be attentive to this. I'll give you certain condition. And the first condition is partial pressure of H2S. So in this case, partial pressure of H2S is 1 kPa. Chloride can be anything, maybe very high. Any means it can be of any percentage. So you can consider a high chloride percentage. pH value is more than 3.5. Cyanides are absent. There is no cyanide. Temperature is 120 degrees Celsius. Okay. Now, which material do you think will be good for this application? low partial pressure of H2S, you have any amount of chloride, pH value is more than 3.5, there is no cyanide, temperature is 180, 120 degrees Celsius. Which one do you think is the right material? I can see almost all the options, okay, in the chat. Okay, I can see all the different options. Now, what is the right answer? Okay, so anytime you will be starting always with a carbon steel, okay, unless there is something which is limiting that uses of carbon steel. Do you find anything limiting here for carbon steel? Do you think something is limiting the uses of carbon steel? Temperature? Cyanide is not there, Arif. 1 kPa is not very high value. 0.3 kPa or greater is where your NACE starts. Okay. So up to 10 kPa, you can definitely use carbon steel. Okay. Now, because the pressure is low, even little bit high temperature, like 180 to 20 is kind of middle temperature, you can use carbon steel. So carbon steel will be the first choice for use in this low pressure, low partial pressure of H2S. So your choice will be carbon steel for this application. Okay. Hold on, if you're a little bit confused, just hold on, because once we see about other material also, then we'll be able to appreciate. So low partial pressure, you may have chloride. Chloride does not create any problem for carbon steel. pH value less than 3.5 becomes really tricky for carbon steel. So in this case, it's greater. So that is also okay. Cyanides also create problem for carbon steel. That is not there. Okay. If your pH value is very high, like if you're going into the basic zone, then high temperature and cyanide presence may create lots of trouble for carbon steel. Okay. So again, that is no. But here you consider that it is in acidic zone. Okay. So even up to, pressure is 1 kPa, so 120 degrees Celsius, there is no problem. You can use carbon steel, P number 1. Okay. Now moving to the next example. Now H2S partial pressure is 100 kPa, kind of high. Chloride 800 ppm may be considered low. pH 3.5, pH is unchanged. Cyanide is not there. Temperature again 120 degrees Celsius. We'll come to that, Vimal. Now tell me for this, what do you think will be the partial pressure of H2S? 100 kPa. It's almost no for carbon steel. Okay, we saw that for carbon steel 100 kPa is kind of upper limit. Okay, you cannot go more than that. It's very difficult to use carbon steel above that. So A is a no. For using stainless steel, what is the limitation? What is the main thing which limits uses of SS? Chloride. Chloride is very problematic for SS. So here 800 ppm. Okay, now you may not be able to say whether it is high or low. Okay, so we'll give you one hint after this, that what is the variation which may be possible. So we'll talk about that also. But now consider for 100 kPa and pH value and the temperature. Okay, all are taking part. Even the small variation of temperature may limit the uses. Okay. So for this, at 120 degrees Celsius, 100 kPa H2S partial pressure, chloride 800 ppm, 3.5 pH value, stainless steel 316L. I'm not talking about 304. Okay. 304 may not be good for this. 316L will be a suitable selection of material. Okay. Now, okay, still the stainless steel application may not be very clear. So let me just build upon that. Okay. Don't write anything. So let us build. Okay. Now what happens? Let us change the 120 degrees Celsius temperature a little bit. Let us make it 150. From 120, I have changed the temperature to 150. Now, do you think it can take 100 kPa partial pressure at that, even 30-degree variation? The partial pressure of H2S, you can see the limit. Notice the change. From 100 kPa, directly it will go down to 10 kPa. If I change the temperature from one, see, I'm playing at the limits. Okay. So 150 degrees Celsius is the limit if my partial pressure is 10 kPa, okay, of H2S. So if I increase the temperature just by 30 degrees Celsius, okay, from 100 directly, I'll come back to 10 kPa. I will not be able to take more pressure than that. Okay. Now, first part is done. Still, it is stainless steel only. We are talking about the uses of stainless steel. Okay. Now, let us play with the chloride. If my chloride content, if I'm changing from 800 to 50 ppm, okay, I'm changing it to 50 ppm. In that case, you don't have any limit on either temperature, pH, or H2S for the use of 316L. Definitely carbon steel I can use for this, but here I'm talking about the uses of stainless steel. Okay, just to give you an idea of its uses. So if chloride content is less than 50 ppm, definitely carbon steel is a better choice. But if temperature is high, then carbon steel you won't be able to select. Then you can select SS because there is no limit on the temperature if the chloride content is less than 50 ppm. Does it make sense? There is no limit on the partial pressure of H2S. There is no limit on the pH. There is no limit on the temperature. If my chloride content is less than 50 ppm, I can use stainless steel at any H2S pressure, any pH value, or any temperature. Does it make sense to all of you? Does it make sense? Okay. So I'm taking very few examples, Rajan. Okay. I'll not be covering everything because otherwise it will become confusing. So I'm trying to draw some lines for the uses. 304 is very less used. Okay. The limitations are much higher on that. 316L you can use for wide application. Okay. Now taking the third example. Now you have very high chloride concentration and the temperature is also high. So H2S partial pressure is 20 kPa. Chloride content is 1,80,000. Okay, very high chloride. pH value, it may be anything. Cyanide is not there. Temperature is also high, 200 degrees Celsius. What is the material which you'll be selecting? What is the material which you'll be selecting? See, definitely D is kind of for everything, So D will be when you cannot select C or B or A, right? So nickel, definitely, that will be end because you will be selecting when you cannot select any other material. Okay. So we'll have to think whether I can use 316L. So we saw that limit, for 150 degrees Celsius, only up to 50 ppm I can go. Okay. So high temperature, it cannot take. High temperature and chloride, SS cannot take. Okay. If the chloride content is much lower, then you can, use SS. Okay. So in this case, you'll go with duplex. Okay. So up to 200 degrees Celsius, and partial pressure of H2S is not very high. Okay. Still, it is in lower case, or you can say that medium. Okay. You'll not say lower for NACE application. It's in the medium case. Okay. So 20 kPa, 200 degrees Celsius, you can go up to 1,80,000 partial ppm of chloride. Okay. Now this I'm taking from definitely the code or standard 175. So at this you can use, so very high chloride, your selection will be duplex, unless you have cyanide also present, or the partial pressure of H2S is more than 20 kPa. Okay. If it is goes beyond 20 kPa, then you won't be able to use duplex. Then only one choice will be there, that nickel alloy. Okay. So that is for third. Now the final one, from 20, I have just changed to 25 kPa. Chloride even, I'll bring down to lower value. There may be cyanide also. Okay. Then what you'll be using is nickel alloy. Okay. Because cyanide, the nickel alloy is the material which is comfortable, because for high pH value and cyanide, that is a no-no for carbon steel. Okay. pH value is high and cyanide presence becomes, you cannot use carbon steel. 304 cannot be used for such a high chloride content. Okay. Duplex beyond 20 kPa, you cannot use for 120 degrees Celsius. So only thing which is left is duplex. Okay. Now, definitely for few of you, at least you might have drawn at least some boundaries, some understanding might have happened. That is good enough. Okay. Don't worry about it, because NACE is a very, very deep subject and there are so many variations there. That's very difficult to draw a line. But based on whatever is available, I've tried to draw some lines out of it. Okay. So even if you've got 1 or 2 points, that is good to go. Okay. Don't worry. Yes, duplex you can use for lower H2S pressure, Justin. Lower, there is definitely not a problem. Okay. So KKR refinery services where NACE 103 is applicable, there is no history of HIC, or maybe you can say that there is no data available for HIC. So NACE only talks about SSC. Okay. So there is no standard developed for HIC for refinery services. So it is not available. Yeah. So definitely, Swapnil, if material, you find that base material you cannot use, you can do cladding. That is where the cladding of Inconel comes into play. Okay. So you'll see heat exchangers getting cladding. So the reason is this, you want to use nickel alloy, but you don't want to increase the cost by changing the complete base material. So use clad. Okay. So normally, Inconel is used for cladding. You will never use for the complete channel. Right. So definitely there are lots of requirement for clad overlay in that. So I've not tried to cover that in this course, but I've tried to keep it short, specific to, at least give you some thumb points which you can use for the selection.
For in-depth training and to learn more about these courses, register with the link in the description.